Hello and welcome to this SimScale how-to video. My name is Ioannis. I'm a senior application engineer at SimScale, and today we're going to see how to simulate a sheet metal forming part in a SimScale highly nonlinear simulation. Today's example is a sheet metal forming process where we utilize two tools, a punch and a die, and a sheet metal part made out of aluminum. This is a highly nonlinear analysis. We are going to use steel for the tools and elastoplastic material model with multilinear specification for the aluminum. We are solving this into 3 steps, including the tool positioning, the punch, and the retraction to determine the final shape of the sheet metal part. Of course, we are going to use a quarter symmetry of the model to save some time, and we're going to utilize the second order quad elements, which are really good for cases where a lot of bending is taking place. The final outcome of the simulation would be, of course, to determine the final shape of the sheet metal part, but also to compare and measure the reaction force needed to complete the process. We are going to compare this force with benchmark data coming from NAFEMS. Now, moving to SimScale, we open the relevant project and we start by editing the geometry to create the quarter symmetry model, which we're going to use for this simulation. I can simply use 2 split operations to bring the model at the final form. Saving the model and now creating a new simulation, what I need to pick is the nonlinear mechanical Marc analysis, which is really meant for this kind of analysis where high nonlinearity is involved. I create a new simulation and now I can go through the setup to start populating the different fields. The first thing I want to do is I want to create a conduct where I want to create a conduct, a touching conduct between the 3 parts, and also specify the correct friction coefficient that is also set by the NAFEMS benchmark standards. The next thing would be to start creating the material. For the material, I will just use standard steel for the tools, and then I will use aluminum for the sheet metal part. For the aluminum part, I need to change the material load to elastoplastic and utilize the curve, the multilinear curve, into the system. To do that, I simply change the plasticity model to multilinear, and I just drag and drop the curve from my CSV file that I already prepared before the setup process. Moving on next, we can now start setting up the boundary conditions, and we start with the imposed displacement of the bottom part of the die, where we initially just fix it at time 0 and then we move it to the right position during the positioning step, and then we just keep it fixed in place as we wait for the punch to happen. We can also visualize the field, the signal really nicely. We do exactly the same for the punch, where we just apply the same positioning step, and then afterwards we specify another 28.5 millimeter displacement according to the NAFEMS benchmark to do the punching, and then we subsequently retract the tool back to the original position to determine the final shape of the sheet metal part. At this point, we can also now create the load steps. All right, so we create one for positioning, one for the punching process, and another one for the retraction process, each of the load steps taking roughly 1 second to complete. And we are good to go now to create the stabilization for the sheet metal by creating an imposed displacement on one of the faces and fixing all the degrees of freedom during only the initial load step where the positioning happens, so that the part doesn't fly freely in space during this process. Next in the list is the symmetry definition. We can use again imposed displacement in the 2 sides to account for the quarter symmetry effect, and we can of course give relevant naming to the boundary conditions so we can easily distinguish between the rest of the setup. Once we're done with the boundary conditions, we can now start populating the solution fields where the user can ask for extra results. For example, the equivalent plastic strain is a quite relevant result for the simulation where we expect high deformation and plastification. And of course, the contact pressure at the contact results is another result that might be really interesting for the users in this case. Apart from these two, because we're also interested in the total reaction force needed to perform this punching, we can create the surface and area average sum of the reaction force and put it on the moving surface of the punch to help us calculate the total reaction force throughout the whole simulation process and on every time step and plot it as a nice graph at the end. Cool. When we're now done with that, we can proceed with the meshing, and we're gonna use the extrusion mesh refinement to generate a second order quad dominant mesh across the tools and the sheet metal. We can specify the number of elements, the thickness, and the maximum sizing, and we can do the same for all the parts. When we're done, we generate the mesh, and in a few minutes, we can see the mesh is ready for inspection, where we can see the really nice quad mesh generated. And we can inspect in the event log things like a total node count, element quality, element type, etc. The mesh looks good. We are good to now finish the simulation setup by setting the total time to 3 in the simulation control and adjusting the minimum initial and the maximum time step that's gonna be used in this simulation. Perfect. We are now ready to run the simulation. We started, and this is now on the cloud. And within a few minutes, you can see the progress is already at 60%. To save some time, we'll just jump directly in a finished simulation where we can post-process the results really quickly. So here you can see I created this nice animation of the whole process that shows exactly the final shape of the sheet metal part. I can change the coloring to plastic strain, for example, to visualize the different plastification regions. I can move the slider left to right to align it to the right time step I need to visualize. I can show the mesh, and I can also plot the total reaction force and find the maximum which is there. Remember, we need to do this force times 4 to account for the full model because we were solving only a quarter symmetry model. And indeed, there you go. When we do the math and we calculate the total force, we can see that we match really closely the benchmark results coming from NAFEMS. SimScale follows really closely the whole trend and predicts the peak quite accurately, I would say, which leaves us with the fact that we were able to produce a really nice simulation within just a few minutes of setup and simulation time using the power of the cloud. Thanks for watching.